Ever wondered what makes a machine learning model go from good to great? It's not just the data or the algorithm itself. Often, the secret lies in a set of special knobs and dials that we, the developers, get to control. These are called hyperparameters, and understanding them is crucial for building powerful AI. So, what exactly are they, and how do they differ from the parameters a model learns on its own? Unlike model parameters, like the weights in a neural network that are automatically adjusted during training, hyperparameters are set by you before the training process even begins. Think of it like this. If training a model is like baking a cake, the model parameters are how the cake rises and browns in the oven. The hyperparameters are your recipe choices, the oven temperature, the baking time, and the amount of sugar you decide to use beforehand. These choices will ultimately determine how well your cake turns out. At the core of machine learning, hyperparameters define the high-level structure and behavior of your model. They are the settings that you, the data scientist or engineer, configure to guide the learning process. There are many different types, and their importance can vary depending on the algorithm you're using. Some of the most common examples include the learning rate, which controls how much the model's parameters are updated in each step. Another key hyperparameter is the number of hidden layers in a neural network, which determines its complexity and capacity to learn. We also have to choose activation functions, like ReLU or sigmoid, which decide whether a neuron should be activated or not. Even the number of training cycles, or epochs, is a hyperparameter. Getting these settings right is a foundational step toward achieving optimal performance. So, how do we find the best combination of these settings? We can't just guess. This is where hyperparameter tuning techniques come in. Let's visualize a few popular methods. First, there's grid search. Imagine a grid where each axis represents a different hyperparameter, like learning rate and the number of layers. Grid search systematically tests every single combination on that grid to find the one that performs best. It's thorough, but it can be incredibly slow and computationally expensive. A more efficient alternative is random search. Instead of trying every combination, random search randomly samples a set number of combinations from the hyperparameter space. It's often faster and can surprisingly yield results just as good as grid search, especially when some hyperparameters are more important than others. For an even smarter approach, we have Bayesian optimization. This method uses the results from previous trials to make an informed decision about which combination to try next. It builds a probabilistic model of the objective function and uses it to select the most promising hyperparameters, making the search process much more efficient. The practical impact of tuning these settings is enormous. Let's take the learning rate as an example. If you set the learning rate too high, the model's training can become unstable, bouncing around wildly and failing to find the best solution. It's like taking giant, clumsy steps down a hill and overshooting the bottom every time. On the other hand, if the learning rate is too low, training will be painfully slow, taking tiny, cautious steps. It might get stuck in a suboptimal solution or take forever to reach the best one. But when you find that just right learning rate, the model converges smoothly and efficiently, quickly landing on an optimal set of parameters. This balance is what we strive for, and visualizing this process shows just how critical a single hyperparameter can be to the success of your model. To wrap things up, we've seen that hyperparameters are the configuration settings you define before training a model. They are distinct from the parameters learned from data and include choices like the learning rate and network architecture. By using systematic tuning techniques such as grid search, random search, and Bayesian optimization, we can navigate the complex space of possible settings to find the best combination for our specific problem. Ultimately, mastering the art of hyperparameter tuning is not just a technical exercise. It's a fundamental skill that unlocks the true potential of any machine learning model, turning a promising algorithm into a high-performing, real-world solution.